So to graph f of x equals 2 to the negative x minus 2, we first want to decide what our parent function is. So start by identifying what the base is for this function. In this case, the base is 2. Remember, the base is whatever number is being raised to the exponent. So our base is a 2. So everything else here is going to be either a shift, a reflection, or a stretch. So that tells us that the minus 2 is going to impact our graph, and then the negative in front of the x is also going to impact our graph. So if you get rid of the minus 2 and you get rid of the negative in front of the x, you're left with your parent function, which is y equals 2, your base is 2 raised to the x power. So that's what we're going to focus on graphing first. And then we'll take that graph and we'll apply our transformations. Remember, I always recommend that you shift last. So first, let's talk about the negative in front of x. So remember, if we're making our x values negative, then that means we will be reflecting over the y-axis. Reflecting over the y-axis will be our first transformation. And then we have a minus 2, and that's going to take our entire graph and shift it down 2. So we have our parent function and we have our two transformations. So now let's focus on graphing the parent function first. When you're just starting out, if you need to go ahead and make a table to help you graph the parent function, that's fine. You just want to eventually move towards not having to make a table anymore. So for example, going ahead and inputting values from -2 to 2 would be fine to help you graph the parent function. So y equals 2 to the x power. If we're taking 2 to the -2 power, that would give us 1 over 4. 2 to the -1st power would be 1 over 2. 2 to the 0 is 1. 2 to the 1st is 2. And 2 to the 2nd is 4. So let's plot those points to get us our parent function. You probably have room to go ahead and input an x value of 3. So remember, if we did go to x equals 3, 2 cubed, our y value would be 8. And then connect these all with a smooth curve, and we extend because we know that it has a domain of all real numbers. So it extends to the left and the right forever. Notice this is our parent function. Notice the 4 commonalities we talked about before. The y-intercept on the parent function is 1. It has a domain of all reals, and right now our range is from 0 to infinity, and it has a horizontal asymptote. So now we're going to take all of these points and we're going to reflect them over the y-axis. So step 1 I will do in green. So if you reflect over the y-axis, the y-intercept does not change, but everybody else is just jumping directly across the y-axis for the reflection. Notice also that the horizontal asymptote hasn't changed yet by doing the reflection. So what I have graphed here in green is essentially y equals 2 to the -x power. You'll notice that in green this is the same as y equals 1/2 to the x power. And then lastly, we're going to take all of these points and move them down 2, which I'll do in red. I like to move the asymptote first. So think that you used to have an asymptote of y equals 0, so if your asymptote moves down 2, then that means we have a new asymptote down here, and the equation for our new asymptote would be y equals -2. I like to always graph the new asymptote right away, and then just take each point and shift them straight down, down 2. And the nice part about graphing the asymptote is you really don't have to worry about graphing the fractional values, because if you have the asymptote, then you know that the graph has to cruise along the asymptote and get very, very close to it. It has to hug the asymptote. There's really no need to plot those fractional values as long as you have at least 3 other good points on your graph. And then either star or just mark your final graph as f of x so that you know, okay, this is the actual final answer for my graph. So now let's determine the domain and the range for our final answer, f of x, which is what I have graphed in red. So, domain. Well, again, if you look at the original function, you could actually determine the domain without our graph, because look at where x is. X is the exponent, and the exponent can be any real number. Our graph supports this because our graph goes to the left forever and the right forever. So our domain would be all reals. Our range, however, has changed because our parent function was shifted down too. So from lowest to highest, then our range would have to be from -2 up to positive infinity. But we're not going to include the -2 because that's the horizontal asymptote. And the equation for that horizontal asymptote is y equals -2.